Have you ever stopped to think that the GPS technology in your cell phone only works because a patent clerk, over a century ago, questioned something everyone took for granted? What if time wasn't absolute? What if what we call now wasn't the same now for someone in motion? In 1905, while processing patent applications in Bern, a young man named Albert Einstein ignited an intellectual revolution that would forever change our understanding of the cosmos. Without a sophisticated laboratory, without a research team, armed only with his extraordinary imagination and a pencil, he redefined the fundamental concepts of time, space, matter, and energy. If you are fascinated by how great ideas can arise in the most unlikely places and how the curiosity of a single mind can change the course of civilization, this is a journey that will broaden your horizons. Let's explore how Einstein, working on the fringes of the scientific establishment, developed theories that not only revolutionized physics but also shaped our modern technology and philosophical view of the universe. In 1905, while the scientific world buzzed in the great laboratories and universities of Europe, a 26-year-old young man silently worked at a small desk at the patent office of Bern, Switzerland. Anyone looking at Albert Einstein at that time would hardly imagine they were facing the mind that would transform our understanding of the universe. He wasn't a university professor, didn't lead a prestigious lab, nor did he have assistants or sophisticated equipment. He was just a third-class patent clerk with a physics and mathematics teaching degree, which he barely managed to obtain after much academic difficulty. And yet, it was there, in that unlikely environment, that one of the greatest scientific revolutions in human history was born. "My work at the patent office was a blessing for me," Einstein would write years later. And it's not hard to see why. While reviewing patents for clock synchronization, devices and electromagnetic contraptions, Einstein had time to ponder fundamental questions about time, space, and light. The routine work demanded precision and logical rigor, but left his mind free to explore the mysteries of the cosmos. It's almost a paradox. While he helped to register the small technological innovations of his day, Einstein was preparing himself for a discovery that would transcend technology itself and redefine our very existence in the universe. The year 1905 would become known as Einstein's Annus Mirabilis, the miracle year. In just a few months, he published 5 scientific papers that shook the foundations of physics. One explained the photoelectric effect, which would later earn him the Nobel Prize. Another provided definitive evidence for the existence of atoms. A third introduced the equivalence of mass and energy in the famous equation EMC2, and 2 others presented the special theory of relativity. Like a burst of scientific creativity, these publications emerged not from elaborate experiments, but from thought experiments, hypothetical scenarios that Einstein envisioned with almost cinematic clarity. Imagine the scene: Einstein returning home after a day at the patent office, boarding an electric tram, a relatively new technology at the time, and looking at the clock tower of the city. Suddenly, a question arises in his mind. What would happen if this tram moved away from the clock tower at the speed of light? Would the clock's hand appear frozen? This seemingly simple curiosity contained the seed of a scientific revolution. Einstein wasn't satisfied with the existing explanations for how light behaved or how we measured time and space. For him, there were fundamental inconsistencies that needed to be resolved, even if that meant challenging the principles set forth by Isaac Newton, which had dominated physics for more than 2 centuries. Einstein's brilliance lay not just in his exceptional intelligence, but in his willingness to question the unquestionable. While most scientists tried to fit new discoveries into the existing Newtonian physics framework, Einstein had the courage to ask, what if the very notions of absolute time and space are wrong? This revolutionary approach didn't come from nowhere. It was fueled by years of contemplation, readings of works by physicists like Maxwell and Lorentz, and discussions with friends like Michel Besso. But it was Einstein's unique ability to simplify complex problems down to their essence that enabled his breakthrough. As he himself would say, if you can't explain something simply, you don't understand it well enough. This search for elegant simplicity behind the universe's apparent complexity would be the hallmark of his entire scientific career. When Einstein proposed that time does not flow uniformly for all observers, He was challenging not only established physics, but our own intuition about how the world works. Put your hand on a hot stove for a minute, and it seems like an hour. Sit with a pretty girl for an hour, and it seems like a minute. That's relativity, he joked, simplifying a deeply complex concept. But the real revolution went far beyond this humor. Einstein mathematically demonstrated two observers in relative motion would experience time differently, a phenomenon known as time dilation. A moving clock seems to run slower when observed by someone at rest. And this is not an optical illusion or a perception error, but a fundamental physical reality. Consider this. You're standing at a station while a train speeds by. Inside the train, a passenger turns on a flashlight and points the beam at the ceiling, seeing it move in a straight vertical line. But from your point of view outside the train, you'd see this same beam trace a diagonal path, since the train continues to move forward while the light travels. Here's the crucial point. According to classical physics, you would disagree about the speed of the light. But Einstein postulated something revolutionary. The speed of light is constant for all observers, regardless of their relative movement. To reconcile this constancy with differing observations, something had to give, and that something was our concept of absolute time and space. The equation E-REMC2 is perhaps the most famous scientific formula in history, but few truly grasp its revolutionary significance. It establishes an equivalence between mass and energy, concepts previously considered completely distinct. This equivalence implies that even a small amount of mass can be converted into a huge amount of energy, as we see in nuclear reactions. But it also means something deeper. Matter and energy are different manifestations of the same thing. As Einstein explained, mass and energy are simply different aspects of the same concept. This unification of seemingly separate concepts would be a hallmark of Einsteinian thought and a fundamental feature of how the universe actually works. 10 years after his special relativity theory, Einstein expanded his ideas to include gravity, creating the general theory of relativity. Here he proposed something even more revolutionary. Gravity is not a force acting at a distance, as Newton had described, but a curvature in the very fabric of space-time caused by the presence of mass and energy. Imagine placing a bowling ball on a mattress. It creates a depression, and any smaller object rolling nearby will follow a curved path due to this dip. In the same way, the sun curves space-time around it, and the planets follow these curves in their orbits. This reconceptualization of gravity represented one of the greatest conceptual revolutions in the history of science. The beauty of Einstein's theory lies in its ability to explain phenomena that Newtonian physics couldn't, such as small anomalies in Mercury's orbit. But its true greatness was revealed in 1919, when an expedition led by Arthur Eddington observed, during a solar eclipse, that starlight was indeed bent by the sun's mass, exactly as Einstein had predicted. The theoretical physicist had not only proposed a new theory, but made verifiable predictions that confirmed it. The New York Times headline announced, "Lights all askew in the heavens, Einstein's theory triumphs." Overnight, Einstein was transformed from an obscure theoretical physicist into a global celebrity, and his theory moved from mathematical speculation to a new fundamental description of reality. The Newtonian universe, which had reigned supreme for over 2 centuries, had been surpassed by a deeper and more comprehensive view of the cosmos's nature. Einstein's theories did not remain confined to academic circles. They overflowed into the technology that shapes our modern civilization. When you use GPS on your smartphone to navigate, you are witnessing relativity in action. The satellites that make up the GPS system orbit Earth at speeds of about 14,000 km/h and are subject to a weaker gravitational field than on the planet's surface. According to relativity, their atomic clocks tick slightly faster than clocks on Earth, about 38 microseconds per day. It may seem insignificant, but without relativistic corrections, positioning errors would accumulate at a rate of about 10 kilometers per day, making the system completely useless within hours. Each time you arrive precisely at your destination, you're experiencing concrete proof of Einstein's theory. The famous E-RMC2 equation paved the way for the nuclear age, with all its promises and dangers. Although Einstein never worked directly on the development of nuclear weapons, His equation provided the theoretical foundation for understanding how small amounts of mass could unleash devastating energy. When the first atom bomb was detonated in 1945, Einstein expressed deep regret for his indirect role, declaring, "Had I known that the Germans would not succeed in developing an atomic bomb, I would never have lifted a finger." This ambivalence reflects the complex ethical implications of scientific discoveries. On the other hand, the same understanding of mass energy equivalence has enabled medical breakthroughs such as positron emission tomography, PET scan, which saves countless lives by detecting cancer and other diseases at early stages. Einstein's impact transcended physics and technology, penetrating deeply into our culture. His iconic image, disheveled hair, dreamy expression, and trademark, mustache, became synonymous with scientific genius. His phrase, "imagination is more important than knowledge," inspires both artists and scientists alike. On a deeper level, his theories challenged our perception of reality, influencing artistic movements such as Cubism, which sought to represent objects from multiple perspectives simultaneously, a visual parallel with relativity of time and space. As art historian Arthur the Search Miller noted, Einstein and Picasso, each in his own way, broke with conventional notions of time and space. Relativity also permeated literature, philosophy, and even theology, forcing us to question core concepts like simultaneity, causality, and the nature of existence. Einstein's revolution continues to expand and evolve. The detection of gravitational waves in 2015, ripples in spacetime predicted by Einstein a century earlier, confirmed another aspect of his theory and opened a new window to observe the universe. Black holes, another prediction of his. Equations once considered merely a mathematical curiosity are now objects of intense astronomical study, with the first direct image captured in 2019. The search for the unification of nature's fundamental forces, the unrealized dream of Einstein's final years, continues to motivate generations of theoretical physicists. As physicist Brian Greene observed, Einstein not only transformed our understanding of the universe, he set the agenda for theoretical physics for the following century. Perhaps Einstein's most profound legacy is the way he taught us to think about the scientific process itself. His thought experiment approach demonstrated the power of theoretical reasoning and imagination in science. His willingness to question established truths reminds us that scientific progress often requires challenging consensus, and his quest for elegant, unifying theories reflects a deep belief in the comprehensibility of the cosmos. The most incomprehensible thing about the universe is that it is comprehensible, Einstein observed, expressing awe at the discovery that the mathematical language can so precisely describe physical reality. This captures the essence of the scientific endeavor, the ongoing quest to unravel the universe's mysteries through exploration, curiosity, and creative thinking.